Understanding. In this channel you will get both knowledge and understanding about various topics.
The next is the alkylation. And we will see the Friedel-Crafts alkylation. So what is Friedel-Crafts alkylation? This is another example of the electrophilic substitution reactions. This was proposed by the French chemist Charles Friedel in 1877, and his American collaborator James M. Croft. Both of these guys have, these scientists have discovered a new method for the preparation of the alkyl benzene starting from the benzene. These reactions are now generally called as the Friedel and Crafts reaction, Friedel-Crafts alkylation and acylation reaction. Depending upon the group, if we have used the alkyl group, we call that as the alkylation. If we are using the acyl halide, then we call it as the acylation reaction. The general mechanism you can see here, as I have shared with you the PowerPoint. You can see on that PowerPoint the slide number 39. There's a general mechanism given where a benzene has been reacted with the RX group. RX means alkyl halide group. So it could be any alkyl halide, but most favorably the alkyl bromide or alkyl chloride. This happens in presence of the Lewis acid, and I already told you about the function of the Lewis acid in these conditions. Lewis acid is going to polarize this RX bond. Now it's a little bit polarized, but in order to make it more polarized, it is being treated with the Lewis acid. So there will be a respective Lewis acid. For instance, if I am using the alkyl bromide, then I will be using aluminium bromide, AlBr3. If I am using the RCl group, then there will be AlCl3. So the ultimate reaction will result into the alkyl benzene. That alkyl group will be attached to the benzene ring through the electrophilic substitution reaction. Now what is the overall mechanism for this reaction? You can see that in the mechanism that the chlorine, that you can see that there is a, if we are using the tertiary alkyl halide, this tertiary alkyl halide can react, the lone pair of the chloride is moving towards the aluminium, because aluminium is the electron deficient center. After doing this, what happens, there is a little an intermediate formation where there is a bond formation between the aluminium, the Cl group. So you can see that a positive charge has to come on the chlorine. Now in order to subside this positive charge, there are two options left. Either the chlorine regain the electron pair from the aluminium side or from the alkyl side. But aluminium, since it is electron deficient, and this aluminium Cl bond is more stronger than the Cl-CH bond. That's why the electron pair is pushed towards the aluminium, and we have the formation of another intermediate that is called AlCl4 negative, and there is a carbocation formation, secondary carbocation formation. Now what happens in the next step? The benzene ring attack on the tertiary carbocation, and there is another carbocation formations where the aromaticity has been lost. The electron pair of the benzene has been pushed towards this electron deficient carbocation, tertiary carbocation, and there is a carbocation formation where in the benzene ring, and there is also a loss of the aromaticity. So this is an intermediate. Uh, Now what happened next? Benzene has to regain its aromaticity. This will be the most stabilizing factor here. That's why the proton at this position is now being abstracted by that chloride of the AlCl4 negative. So one of the chloride abstract the hydrogen, changes it into the HCl molecule. The AlCl4 is now left as AlCl3 as a neutral molecule, and the electron pair, bond pair of the hydrogen is now shifted towards the benzene again, and then we have this aromatic ring regenerated again. So benzene molecule, there is a formation of the benzene molecule, benzene ring again, and along with that benzene we have now, instead of the hydrogen, at the sacrifice of the hydrogen, now an alkyl group has very simple examples, and then this kind of the reactions you are already familiar with. You have studied this thoroughly in detail in the at the FSC level. There's nothing special about it at this stage to discuss. One thing that will be new for you at this stage is that whenever you are treating the alkyl halide I mean, if you are treating the kind of alkyl halide that is secondary or tertiary, where the carbocation can exist independently for a little while, then there will be a carbocation formation, and then benzene has to come and will attack the carbocation. But if you are treating with the primary alkyl halide, in case of the primary alkyl halide, there is no formation of the carbocation. Instead, the when you are attacking the that alkyl halide with the aluminium chloride, instead of the aluminium push the electron, abstract the electron atom, chlorine atom from the alkyl halide and produce the carbocation, there, instead of this, there will be a formation of a complex. There will be a formation of what? Complex. What is that complex? That complex is there will be you can show that with the dotted line, where there is a R is the alkyl group, CH2 is that carbon where the carbocation has to be produced, and that carbocation is attached with the aluminium with the chlorine of the with the aluminium. So you can see that the overall transition state would show RCH2 dotted line dotted Cl dotted AlCl3. So you can see that they will remain, all this complex will remain intact, and they will remain as such unless it is attacked being the by the benzene ring. Benzene, when attack this complex at this stage, instead it is being separated into a carbocation and the aluminium chloride. Benzene ring would preferably would like and will attack on the complex. After the attack of the benzene on the complex, the aluminium chloride will be left as AlCl4, and the other carbocation will be attached to the benzene ring now at this stage. In the previous example, we saw that secondary carbocation was attacking, and before attacking of the benzene, there was an initial formation of the carbocation, a clear carbocation formation. Why? Because that carbocation can exist in that form. That was stable because that was secondary. Same is the case with tertiary. But once you are dealing with the primary carbocation, the benzene ring will be attacking on the complex rather than on the carbocation. Now there is a there will be attack on the carbocation, but this carbocation will be connected to the complex. Under that condition, the benzene has to attack on the complex, pushing the aluminium chloride on the other side and absorbing that carbocation, primary carbocation along with that alkyl groups, and then thereafter there will be a loss of the aromaticity, and then that aluminum tetrachloride will, one of the chlorine of the aluminum tetrachloride will abstract the proton, and then after the abstraction of proton, there will be an HCl formation, and there will be an formation of the AlCl3 that will be regenerated, and finally we would have the carbocation attached to the benzene ring, and there will be a regain of the aromaticity. So the overall step is that we will be having alkyl group, primary alkyl group will be attached to the benzene ring. There is a little bit change in the mechanistic pathway for the primary and for the tertiary and secondary alkyl halide, because in secondary and primary in secondary and tertiary alkyl halide we have the carbocation formation. This is a clear carbocation formation, while in case of the primary alkyl halide we have a complex formation, and this complex is being attacked by the benzene ring, and then the overall thing is the same. There is always, whether that is the primary or the secondary or the tertiary, there will be the attachment or the attachment of the alkyl group. Same wise you can try some more examples using the tertiary alkyl halide with the AlCl3, and then you can write the mechanism for that as well, following the same procedure using the aluminium chloride as a Lewis acid, and the overall step they are all the same, whether that is the aluminium chloride protonation step, formation of the carbocation, and there is a formation of the valent intermediate forms. So all these are the same for the. So what about the is there any limitation for the Friedel-Crafts alkylation? Can you please tell me what are the kind of the limitations? Limitation of the Friedel-Crafts reaction is that we can only produce the alkyl halide, only the alkyl halide can be used, such as the fluorine, chlorine, iodine, and bromine. And another thing is that aryl halide and vinylic halides do not react because their carbocations are very unstable, and they are usually not formed during the reactions. So aryl halide and the vinyl halide do not react and do not work for the Friedel-Crafts reactions, because their carbocations, they are unstable, and once the carbocation is unstable, they wouldn't react. One other new thing about the Friedel-Crafts alkylation reaction that maybe you are not familiar with yet, that will be new thing for you, is the control problem. I mean, how to control the alkylations, because you know you have this aluminium chloride and you have this alkyl group. So if the alkylation happens once, it can also occur again. So how you would be able to control that? Sometimes the control is very difficult. That's why you have the major and minor products. Most of the time, if there's a possibility of the product, further product formation, then the reaction will definitely go into that, towards that. This is same just like the as you have studied about the hydrogenation of alkyne, where you can't stop the hydrogenation at the alkene stage unless you use the Lindlar catalyst, because the reaction has to go towards the hydrogenation will be continued till the alkane. Same you have studied about in the halogen Friedel-Crafts, the free radical reactions of the alkane, where you saw that the initial propagating step moving towards the terminating step, replacing all the hydrogen. You can stop that at once if you are using less number of the equivalent of chlorine. But if you are not controlling that, that reaction has to go towards end. Same is the case here in the Friedel-Crafts alkylation, that it would be difficult for you to stop the reactions if you are not withdrawing the aluminium chloride, the alkyl groups or the reagent. Then it has to go towards the and further substitutions. You can see in this example at the slide number 45 that one time this tertiary carbocation is produced, and then there is a mono substitution where the alkyl group, tertiary alkyl group, is substituted at the benzene ring, replacing the hydrogen by the same mechanism as we have discussed above. And then the same thing can happen again, because this one time this tertiary alkyl group is attached to the benzene ring. You already know that this is the ortho and para director, so the coming electrophile will definitely be pushed towards the para position. So under that condition we will have two products. One would be the one where there is a single substituted product, I mean a single alkyl group substituted at the benzene ring. This will be the minor product, and the major product would be the one where there's a two alkyl substitution, both para to each other, and we'll also be having somewhere the unreactive benzene as well. So they are the kind of the side products along with the major product, that is the bi-substituted alkyl group. Benzene 2 of the hydrogen of benzene has been replaced with this electrophile. You can see that the N-pentyl chloride is going to react with the benzene ring in presence of the aluminium chloride at 0 degree centigrade. Here you can see that the instead of the product that we were expecting, that the N-pentane ring will be attached to the benzene ring. That is the minor product you can see on slide number 46. The major product is the one where the carbocation has been produced at the secondary carbon. I mean before reacting, before going this reaction towards the product, firstly there is an internal rearrangement at the at the alkyl halide. You can see that on the slide number 47, where after the carbocation formation, the primary carbocation is now changing to the secondary carbocation by the migration of that methyl group. By doing that, the carbocation is now secondary in nature, or tertiary in nature. So the tertiary carbocation is now more stable, and the tertiary carbocation, you can see that can react most easily. Slide number 47. But if you look at the slide number 46, where the N-pentyl chloride has been treated, so in this N-pentyl chloride you can see that instead of the primary carbocation, there is a formation of the secondary carbocation. Why? Because the secondary carbocation is more stable, so there is a migration of the methyl group to one other position. Is there a migration of the methyl group or the hydrogen? So in slide number 46, there is a migration of the hydride, I guess, to produce the secondary carbocation, and then secondary carbocation is now attacked by the benzene ring. So the bottom line is that whenever there is a possibility of the secondary, or there is a possibility of the tertiary carbocation, the reagent would favorably would like to go towards that, because under that condition, the more stable the carbocation, the most favorably the reaction can go towards product, and that will be the most stable major product, the one where the carbocation is being more stable than the other one. What about this product? What about the mechanism for this product formation? You can see here that H3PO3 has been tried. H3PO3 is an acid, and first what this acid will do is it will be the alkene will be abstracting proton. This is now an asymmetric alkene. The proton can be abstracted at the terminal carbon or at the uh, more substituted carbon. But definitely, if the terminal, if the proton is abstracted by the Markovnikov addition, so there will be carbocation formation at the tertiary site, and this is what is happening. There's a tertiary carbocation formation, and then the tertiary carbocation is now easily attacked by the benzene ring, and then there is a rest of the steps, they are the same. There is the regain of the aromaticity by abstraction of this one of the proton by H2PO4, and then again we will be left with that. So there are some more example. You can say that whenever we have alcohol group, you can see that on the slide number 50, where the an alcohol primary, I guess secondary, tertiary alcohol is there. So the tertiary alcohol group firstly abstract the proton from the acid, and then firstly there is a formation of the tertiary carbocation, and then tertiary carbocation is being attacked by the benzene ring and producing that. The next is the acylation reaction of the aromatic rings. There's no major difference between the two, but the only difference is that in alkylation we use the alkyl halide, while in acylation we use the acyl halide. And what this acyl halide is about, it's the RC double bond O Cl group. C double bond O Cl group is called the acyl group. So this acyl group is now being reacted with the benzene ring. This acyl group is attached as an electropile, replacing the hydrogen of the aromatic ring, producing the product. You can try this on a number of examples. For instance, you can try the benzene ring with the CH3 C double bond OCl, that is called the acetyl halide, where the halide group is, you can treat this with the same Lewis acid to make it polarize, and then the overall mechanism seems to be same, just like the alkylations, but there is an acyl group formation, and the benzene ring has to react. So you can see firstly that I will be sharing one of the example with you, that this acyl halide is reacted with AlCl3. This Lewis acid again have the same role, that it is polarizing the bond between the C double bond O and Cl. Though it is already polarized, but it is further polarizing this bond, and then we have the complex formation. That complex is now being so there is one other difference because here there is an acylium ion formation. Acylium ion formation, acylium ion, you already know that it is the RC triple bond O positive. This is called the acylium ion. Acylium ion. So along with the AlCl4 negative, and now this acylium is attacked by the pi electron of the benzene ring, producing that there is the sacrifice of the aromaticity for a while, and then there is a regain of the aromaticity. You can see that mechanism. You will be facing a kind of situation where the instead of giving you the clear acyl halide group, there will be an OH group with the carbonyl group, and if you want to carry on that reaction, first of all you have to change that OH group, which is the bad leaving group, into a good leaving group like the halide group. So there will be an initial pre-treatment before the Friedel-Crafts acylation reaction. And how to do that? You can see that for instance, if you have acetic acid, right? So now if we are trying to react benzene ring with the acetic acid, and then we can expect, and we are expecting that it will give us the product. I mean the acetic group will be acetyl group will be attached to the benzene ring. So this would not happen. This would not happen at all. First there will be a pre-treatment, and that pre-treatment would include the changing of the OH group of the acetic acid into the respective halide group. How to do that? For instance, we will treating the acetic acid with the thionyl chloride or phosphorus pentachloride. Both of these groups can easily change the acetic acid into the acetyl chloride, right? PlCl3 has the same reaction. This changes the acetic acid into acetic halide group. Once we have this acetic acetyl halide, this acetyl halide now can easily be attacked by the benzene ring to produce their respective acetyl group. Same is the case with the acetic. You can also treat that with the acetic anhydride. Acetic anhydride, there is no need, because acetic anhydride is already a very good living group. So this, if you are treating the acetic anhydride with the benzene, then there will be an acetyl group will be attached to the benzene ring. There is no problem with that, because the O acetyl group is a Friedel-Crafts reaction is that what about the electron donating and electron withdrawing group if they are already there with the benzene ring? Whether that will facilitate the Friedel-Crafts alkylation, or it will retard the rate of the reaction? Well, the answer for this reaction is that we are expecting the benzene ring to be more electron rich. If somehow some of the withdrawing group, in fact the powerful withdrawing group, they will greatly reduce the rate of the reaction, because they will pull the electron density of the benzene ring. So benzene would not be able to push its electron towards the electrophile to undergo the electrophilic substitution reaction. I can show that. So tomorrow we will be continuing with the residue selectivity in the Friedel-Crafts alkylation and acylation reaction. It's over for the day, and that's it. I welcome any of your questions right now.
This is the end of this video. Hope you have liked it. So, don't forget to like, comment and share the video. Also click the bell icon for more updates.